Bühler Motor fractional horsepower DC motors, application engineering. Hello, my name is Gerhard Hofmann. Part 4 of the training sessions on application engineering covers the thermal aspects in the motor during operation. All the considerations we have done in the previous sessions assumed static performance curves which do not change during motor operation. In reality, though, the performance curves change due to increasing temperature while the motor is running. The temperature rise is caused by the power losses in the motor, which are completely transferred into heat. This means the lower the motor efficiency at the load point, the greater the temperature increase in the motor. In order to do estimations on the thermal behavior of the motor, we have to calculate the power loss at the load point first. This can easily be done by subtracting the output power from the input power. This means PL is P in minus P out. Physically, this means applied voltage multiplied by load current I sub L minus load torque T multiplied by the angular velocity omega. In order to use the known speed values in RPM, the formula looks like this. The factor P divided by 3000 is necessary if we insert the speed n in rounds per minute and the torque T in Newton centimeter. PL will then have the unit watt. How do the performance curves basically react to temperature changes? Looking at the speed torque and the current torque curve of a cold motor and compare this with a hot motor, we can see significant differences in no-load speed, stall torque, as well as stall current. The characteristic speed regulation constant of the motor is changing with temperature. R sub m of the hot motor is greater than R sub m of the cold motor. The actual temperature the motor sees is defined by the temperature rise due to the power losses plus the temperature of the environment. Performance curves of a 13050-1200 motor at minus 40 degrees C and 150 degrees C are shown here and display the big range the motor covers between the temperature limits. For instance, stall torque varies from around 30 Newton centimeter to almost 100 Newton centimeter. We need to keep this in mind that it is the same motor operated with the same voltage. The change in the motor performance is caused by the permanent magnets and the copper magnet wire. The magnetic properties of the permanent magnets as well as the resistance of the copper is depending on temperature. Magnetic flux is decreasing and resistance of the copper winding is increasing with increasing temperature, and vice versa. Due to these physical impacts, the speed regulation constant Rm is increasing with higher temperatures, which means the motor is getting weaker. In reverse, the speed regulation constant Rm is decreasing with lower temperatures, which means the motor is getting stronger. To recap the aforesaid, here you see the speed torque curves of a specific motor at different temperatures. The knowledge of this behavior of the motor is important for the functionality in the application. The thermal behavior is based on physics and cannot be avoided. It therefore has to be considered during the motor application calculations. The operational conditions as well as space and mounting conditions in the application are of importance for the thermal behavior and therefore have to be known. Usually the temperature of the motor winding is considered to be the limiting factor for our application considerations. To be on the safe side, the limit for the winding temperature should be 150 degrees C. If we now want to do calculations on the motor behavior at certain temperatures, some motor characteristics have to be known. At first, we need to know the thermal resistance RTH of the motor. RTH describes basically the capability of the motor to transform the power losses into heat. The unit of RTH is Kelvin per watt. The next important constant is the thermal time constant, tau TH. It considers the duration of the temperature increase. The unit of tau TH is minutes. The temperature rise in the motor follows an exponential function as shown here. The diagram shows time on the x-axis and temperature on the y-axis. The formula for the temperature rise is 1 minus e to the power of t divided by tau th. The end temperature is the maximum temperature the motor reaches theoretically after infinite time. Practically, the end temperature is reached after 5 times of the thermal time constant tau th. Per definition, at 63.3% of the end temperature, we find the thermal time constant in the graph. Thermal resistance as well as the time constant are depending on the motor size and design. Values are shown in the catalog. Here you see the values for the motor 113049400, where we see the thermal resistance RTH 13 Kelvin per watt and the thermal time constant tau TH with 16 minutes. With the knowledge of the power losses and the thermal resistance, we can calculate the winding temperature of the motor, considering continuous operation at a defined load point. Theta winding continuous is theta environment plus RTH multiplied by the power losses P sub L. The unit is degrees C. Theta winding continuous is the end temperature if the motor runs continuously for an infinite time. Again, the formula for the temperature rise is theta of T is theta winding continuously multiplied by 1 minus e to the power of minus t divided by tau th. We can use this formula to calculate the temperature theta after any time t. We can change the formula to read t equals minus logarithm from 1 minus theta of t divided by theta winding continuous multiplied by tau th. And with this formula, we can calculate after what time t a certain temperature theta is reached. With the formulas shown so far, we assumed a continuous operation of the motor for basically infinite time. If the motor operates with a certain duty cycle, the end temperature of the winding is lower than for continuous operation. The value for the cycle-based end temperature can be calculated if the duty cycle fulfills the following criteria. On time is less or equal off time, and on time is less or equal the thermal time constant tau th. The winding temperature for duty cycle operation therefore is theta winding cycle is theta winding continuous multiplied by the square root of T on divided by T on plus T off. The graph shows the difference in end temperature for the two conditions. For real applications, some estimations have to be made. The thermal constants in the catalog are for the motor only, without any impacts from the application. Is the mounting situation in the application such that the heat can be well dissipated, the RTH value would become lower. Is the mounting situation in the application such that the heat dissipation is poor, the RTH value would become higher. These estimations are based on experience normally. Tests and temperature measurements are therefore oftentimes necessary in order to verify the calculations. To simplify the temperature measurements, the RTH values are split into two characteristic values, RTH1 and RTH2. It is normally not easy to measure the temperature of the winding as the motors are closed. By splitting RTH in RTH1 and RTH2, where RTH1 is the resistance from armature to housing inside, and RTH2 the resistance from housing to the environment, an assumption for the housing temperature can be done. The housing temperature can easily be measured. With the two separate RTH values, we can now calculate the housing temperature. Theta housing is theta environment plus RTH2 divided by RTH1 plus RTH2 multiplied by the power losses P sub L. As a reminder, if RTH1 equals RTH2, the housing temperature is exactly half of the winding temperature. Like in the previous sessions, again a practical example will explain the situation more concrete. We remember the performance curve of the defined motor at 25 degrees C as evaluated in session 1. The load point was T sub L 10 Newton centimeters, N sub L 5000 RPM and I sub L 3 amps. At first we calculate the power losses and the winding temperature. The power losses are, as mentioned before, input power minus output power. In our example, we calculate the input power to 24 volts multiplied by 3 amps and subtract the output power, which is 10 Newton centimeters multiplied by 5000 RPM, multiplied by the factor P divided by 3000. The result for the power losses is 19.6 watt. To calculate the winding temperature, we need the thermal resistance of the 13044 200 motor. The catalog shows a value of 9.5 Kelvin per watt. With this, the winding temperature calculates to 25 degrees C environment plus 9.5 Kelvin per watts multiplied by 19.6 watts power losses. Winding temperature is calculated to 211 degrees C. We calculate the winding temperature at the temperature limits of the specification and see the theoretical range for the winding temperature between 176 degrees C and 256 degrees C. This means that even at the lower temperature limit, the calculated winding temperature would be too high. The mounting situation in the application will now determine the real thermal situation in the motor. In such a case, a temperature measurement on a sample motor, possibly in the application, would be necessary. We remember that the winding temperature should not exceed 150 degrees C. In many cases, the mounting situation in the application helps to reduce the thermal resistance, which results in lower winding temperature. Considering the application conditions help the thermal situation in our example motor, the maximum winding temperature is 150 degrees. We can look at the performance curves at the temperature limits now. One can see that the change in performance of the motor is pretty significant between the temperature limits. This has to be considered when the motor is selected for a specific application. In some cases, it might be necessary to use a bigger motor with lower thermal resistance, or improve the cooling situation in the application, e.g. by adding vent holes. Another possible way would be to run the motor in a cycle mode instead of continuous operation. Have we talked about the definition of a motor for a specific application in session 1 and 2? Prove the functionality at the temperature limits in this session. We will see what impacts are to be considered for the lifetime of the motor in the next session.